They're complementary ideas, I'm not sure.
HD. Okay, so my comments aren't exactly orthogonal. I suspect they're more complementary. But just to summarize some of the main points, the chert mass is about 1.2 solar masses, which means that the minimum total mass is 2.73 solar masses of the inspiraling objects. The limits on tidal polarizability are both 800 either for the binary polarizability or the inferred dimensionless polarizability for 1.4 solar mass stars. The suspicion is that the ejecta mass was 0.05 or 0.06 solar masses. And as we've already seen, I don't want to discuss, but the position of this object in terms of the amount of blue ejecta and red ejecta seems to indicate smaller rather than larger neutron star masses, and perhaps smaller mass ratio than unity. So, from the idea that a black hole eventually forms, and the additional ideas presented just now by Ben that a prompt collapse also did not occur, we can use the fact that there's a nearly universal relationship between the gravitational and baryon masses of neutron stars, something that's relatively independent of the equation of state. And to develop this universal relation, I've done a series of models in which we take a piecewise polytrope equation of state, which is constrained by it having a neutron star crust, and using the results from neutron matter calculations to take us between the crust and about 1.5 or 1.8 times the saturation density. And then above that point, we're limited by causality and also by the fact that we have to produce at least the observed minimum maximum mass from pulsars of 2.01 solar masses. Okay, so as far as the component masses go, the minimum gravitational mass is 2.73 solar masses, and that's in the situation that the mass ratio is unity, in which case the component masses are 1.36, the baryon masses are 1.5, as I'll show in a minute. And this gives a total baryon mass of 3 solar masses. The maximum observed gravitational mass is obtained using the minimum value of Q from the observations estimated to be 0.7, in which case the component masses are 1.64 and 1.15 for gravitational masses. And then the component baryon masses turn out to be 1.85 and 1.25, giving us a total baryon mass of 3.1. So the uncertainty in Q is not leading to a very large difference in the estimates of the baryon mass of the components. So to extract a relationship relating the binding, the amount of binding, we define the binding here as just the difference between the baryon mass and the gravitational mass, and we'll measure it in units of solar masses. And the Timmis relation that Ben used in his last shorthand slide to summarize what he was doing is shown by this red curve. And so near the maximum mass, it breaks down. So a better relationship would be involved this cubic formula shown by the blue line. So each point here represents the binding energy for masses of stars with all kinds of equations of state, limited by the piecewise polytrope ansatz that I'm using, causality, and the ability to make at least 2.01 solar masses. And interestingly, on here I've color-coded stars that have radii of different values. So the ones that lie towards the top have fairly large radii, and the ones that lie near the bottom of this band have small radii, indicating that there's also a radius correlation that's buried in this relationship as well. So instead of having this be a function of gravitational mass, we could add a compactness term as well. And if we limit ourselves to equations of state that produce 2.3 solar masses, maximum mass or greater, we get essentially the same relationship for the blue curve, and again the red curve is showing discrepancies as we go to high, to near the maximum mass. So it doesn't matter what our assumptions are for this binding energy relation, what we assume about what the underlying maximum mass is, as long as it's greater than about 2 solar masses. So if we take into account the ejected mass, the maximum baryon mass of the remnant would be 3.04 solar masses, subtracting 0.06 solar masses, for example. And neglecting any rotational or thermal support, this automatically leads to a gravitational mass of 2.48. So I would argue that this is a maximal estimate for the maximum mass of a neutron, the gravitational mass of a neutron star, because this simply assumes that the entire star, that aside from what was ejected, is present in the remnant, and it eventually decays into a black hole. And this relationship just comes from the binding energy mass relation. So that, I think, sets an absolute upper limit then to the neutron star maximum mass, which is something we didn't have before, except from causality and knowledge of the equation of state up to nuclear densities, which suggested, something in excess, a little bit excess of 3 solar masses. So this is a substantial improvement. Okay, to try to get a lower maximum mass, we do know that the remnant will have considerable angular momentum support. So a series of calculations by Bauswein and Stergioulas indicated that you can find a linear relationship for the amount of angular momentum present in the remnant of an inspiraling binary neutron star, independent of the equation of state and independent of the mass ratio, at least for what they've studied. And they took several different equations of state and several different mass ratios ranging down to about 0.8 or 0.75. That pretty much covers what we're interested in. And this relationship is linear here, where J is given into geometrized units, kilometers squared, and the total mass is given in solar units. So we find from our limits on the gravitational mass that J is between 6.35 and 6.62 square kilometers. And for comparison, typical Keplerian maximum mass configurations have a dimensionless angular momentum divided by the gravitational mass squared of about a half. Now this can be violated and go up to 0.89 as LIGO.
Is that again assuming uniform rotation?
This is uniform rotation, yes. And so this can go up to 0.89. That's the chi of 0.89, I think, that's in LIGO, but only if the radius is 14, 15, 16 kilometers, which I'm going to argue is ruled out. So for reasonable neutron star radii and other aspects of the equation of state, this is basically a generic answer that you get. And so I found, I checked a few papers, but Friedman, Ipser, and Parker have this actually tabulated. Other models, you have to go back and try to work it out. So this implies that this gives us a value of 5.5 kilometers squared in our case, for the 2.73, 2.79 value of the gravitational mass. Okay, so that's smaller than J, indicating that the configuration has to be very close to exceeding breakup. So it's going to be differentially rotating in the beginning. There's no avoiding that argument. And in fact, the hydrodynamical simulations always show differential rotation.
Yeah, no, it's differentially rotating at the beginning. It's a matter of if that's removed, what you have left.
Right. But it's close. I mean, you could support most of the. Okay. So, Lasota and Hansel and company have shown that Keplerian uniform rotation enhances support at about the 18% level. So that the maximum mass for uniform rotation is about 18% bigger than the non-rotating maximum mass. So if extra angular momentum is radiated or transported quickly, and the configuration develops uniform rotation due to the Keplerian velocity, and then later collapses into a black hole, one could argue that the maximum baryon mass then would be on the order of 2.5 solar masses, which implies a gravitational mass of 2.11. So if the configuration quickly moves into uniform rotation, then I would argue that this is a lower limit then to the maximum mass gravitationally, and now we have this bound. Okay? But if in fact you lose so much angular momentum early that you don't have 18% support, but say 10% support, then the lower mass limit would be raised by, say, 2/10 of the solar mass. We begin to squeeze this. So it's very crucial to figure out exactly how much rotational support will exist before the remnant collapses into a black hole. And I don't know how to answer that question yet, but I think this lower limit and this upper limit, the upper limit is certainly, I think, valid, given the assumptions of an eventual collapse to a black hole. And the lower limit depends on assumptions about uniform or differential rotation, and it's less strong. Okay, now radius constraints, we're going to rely on the estimates of binary of deformability. So the definition of the binary deformability is that it's a mass-weighted average of the individual deformabilities, dimensionless, this should have a bar over it, for the two components where the dimensionless deformability is related to the second lobe number, which is also a dimensionless number, which, as was stated, is somewhere between 0.05 and 0.15. So the observations indicate that lambda bar is less than 800, and the individual lambda for 1.4 solar mass stars is also less than 800. Those are in the BRL later letter. And I'll argue that this indicates that the radius of 1.4 solar mass stars has to be less than 13.5 kilometers. And it's interesting that in comparison, neutron matter calculations plus causality implies that the radius of 1.4 solar mass stars is less than 13.1 kilometers. So we haven't improved that limit, but we've corroborated it. So what's interesting to do is to look at the binary, is to look at the individual, the dimensionless tidal polarizability for individual stars, a function of its mass. And I just put a line here, 1.4. And this is for, again, a series of models limited by the piecewise polytrope constraints. And the gaps are because I didn't sample infinitely the mass radius curve, but I selected only a few points along each mass radius curve to draw points. But you can imagine the envelope that you would get if you did infinitely sample it. And again, the color coding shows the radius. So again, there's a pronounced radial dependence in this correlation that you could extract further, which, for example, you can do this. You can divide by the radius to the 6th power and get rid of almost all of the radial dependence there. So if we could measure the individual tidal polarizability in the mass, and even if this was measured to 50%, and if we do the mass to infinite accuracy, then this would tell us we can determine the radius of that star to the 6th power of 50% accuracy. Okay. Because the outer portion here is a 95% confidence interval of all the points up to about 1.6 solar masses. And so the result that we have is that the tidal polarizability for 1.4 solar mass stars was measured is less than 800. So if you take this value of about, 1.2 or 1.3 times 10 to the minus 4, and use 800 in here, you find the radius of 1.4 solar mass stars is less than 13.5 kilometers. So that's how I got that number. But what I find really intriguing is if you plot the binary polarizability, you find an almost identical relation compared to the chirp mass. Now the chirp mass is something that's measured to very high precision, so I drew a line at 1.188, and 800 is the maximum value for that quantity. So it doesn't disallow any, so it's right at a little bit above the upper bound. So it's not quite as good as the neutron matter plus causality constraints that I argued already existed, but it's very, very close. And so if this can be improved, and if we can get a lower limit, even if the lower limits, factor of 3 away from here, we're already limiting things, I think, in a significant way. So I would like to see better estimates of the binary polarizability from this. And again, there's significant radius information here. So here, I've now color-coded each of the points with its 1.4 solar mass radius. So you can form a new combination similarly to the individual tiled polarizability. Take out the 6th power, and you find that everything collapses to almost a line until we get to very large chirp masses. For the chirp mass we have, there's a very small spread here. And again, if you use the value of 800 with this relationship, you again get R 1.4 is 8, the limit is 13.5 kilometers. So that's pretty much all I wanted to say, but I think the tidal polarizability, even from an individual source, is not as pessimistic as I've heard talk, where we need 100 events to say something substantial from the binary polarizability. I think a single event with a reasonable signal to noise, even a 50% measurement of polarizability will give us a substantial radius restriction. So.
This is apropos of the last two talks. You have an estimate for the moment of inertia from
Yes.
pulsars.
Not yet.
Well, I mean, if you believe the magnetic dipole radiation, et cetera,
Yeah, okay, that's
so
a pretty...
I'm just saying it's an estimate.
Right, and hopefully we'll get one from the binary pulsar in a few years.
Can that be used to give you any limits on this?
Absolutely, because the moment of inertia is proportional to the square of the radius.
That's what I'm saying.
So a 10% measurement of the moment of inertia is a 5% measurement.
I mean, how close are they to getting a 10% on the moment?
8 years ago it was 10 years, so I still
Okay.
think it's a few years. But they are making progress. They do have a measurement of the moment of inertia, but the error bars are, factors of 2, so it's not yet useful. But that's not published. That's just sort of private communication. So they do see a value that's consistent with neutron stars, but it's not fine enough yet to give any kind of restrictions on the radius. I mean, it
Because
allows
in
10 to
principle-
15 or...
In principle, that's an independent method.
It's a completely independent method. That's right. That's right.
Questions?
And then there's nicer, and we hope that phase-resolved spectroscopy, the design specification for that is that within a year, we're supposed to have a 5% measurement of both the mass and the radius of a star, helped by the fact that one of the stars has a measured mass because it's in a binary and it's a pulsar.
Questions for Jim? Simone, please.
I was saying just a small thing. So the 2.48 is an estimate of the maximum gravitational mass of the remnant. Assuming that it did collapse, that's an upper limit to
either
the maximum
sooner or
mass.
later.
Okay.
At some point it went into a black hole.
Okay. So then, okay.
And I heard during the press conference the argument that X-rays being observed at 8 or 9 days is an argument that there is now a black hole there. So I don't know quite what that's based on.
Yeah.
Did anybody else hear that?
No.
That was said during the press conference when they discussed the
Yeah,
I
X-rays.
heard that too. Then.
Okay.
I would say the strongest evidence is that we saw a gamma ray burst, and people think that a neutron star would baryon pollute the environment too much to get a relativistic jet. Like, insofar as the X-rays told us there was some relativistic matter, but I would say they're the weaker argument. It would be the gamma ray burst itself, and even that, not everyone agrees about it. So.
Yeah.
Okay, let's thank Jim again. I know everyone is hot, and I don't, and I think most of what I was going to say has been said, but maybe I'll just very quickly sort of just zoom through things and just make a few comments. I